Hello everyone, Anton here. Welcome to the 5th video from the Generative Models in Grasshopper series. The series is part of the Computational Design Basics course by the Digital Design Unit at the Technical University of Darmstadt. In this video we're going to look at evolutionary optimizations. Evolutionary optimizations work similar to the way scientists believe evolution works, which in a nutshell is survival of the fittest. Each organism can be described by its genome or DNA. This DNA expresses in a phenotype, or the way the organism looks and behaves and performs in its environment, which determines its chances of survival. And if the organism has higher chances of survival, it also means it has higher chances of reproduction, which means it can pass its genes further down the generations. So only the fittest get to pass their genes. This concept translates to Grasshopper like this. We can describe a building by a set of numbers, and we call that a genome. Then we have a way to reconstruct the 3D model of that building, of that design. Then we can measure how well it performs on criteria that we've set, and based on that, the evolutionary algorithm will decide, is that individual, is that DNA worth reproducing or not? And when the algorithm decides that a couple of organisms, a couple of individuals, a couple of designs, however you want to call it, are going to reproduce, then it takes their DNA, finds a random point in that DNA where it would cut it, and exchange the DNA material, in that way producing two individuals that are mixed versions of the individuals we had beforehand. And it might also apply a random mutation by changing one of these numbers. This all happens behind the scenes, of course. The component that does that for us in Grasshopper is called Galapagos. There are plugins for evolutionary optimizations that are more powerful than Galapagos. For example, Octopus is one of them. But we are going to use the built-in one, because here it's important to get the principles, and once you get that, you can use also the other plugins as well. So I'm going to start with the definition we saved in the part 4, where we've created optioneering interface to explore thousands of design options of 2 different tower designs. Here's the first tower design that we did, which was modeled after the Sears Tower, and here's the second one, which was these 2 interlocking tubes. And at the beginning we are generating that genome. Then here we are creating the 3D model of each of these designs based on the genome. Then we are evaluating them, so we have our fitness criteria, so to say. And the last part is the optioneering part, which in the workflow with evolutionary optimizations we're actually not going to use. So the way we're going to start is by duplicating, disabling everything, and duplicating the first tower design, the Sears Tower based. Let's take the whole definition in here, and then we'll clean it up. I'm going to zoom in and rename that scribble here to part 5, evolutionary optimization. Evolutionary optimization, Sears Tower. Okay, and let's bring in Galapagos and see what it wants from us as inputs. So Galapagos is actually a quite modestly looking component, but you already recognize it has a different design than everything else. It's pink. It wants the genome as an input. Those will be all the numbers that define the tower heights in that design. And it wants the fitness, or how well the towers are performing here, but it wants only one fitness. So that's something we need to sort out, because we are measuring on 4 criteria. So let's see how we deal with that. And then let's look what's inside. If we double click on the component, we have a couple of tabs. First one is options. Basically, the evolutionary optimization can either minimize or maximize the fitness depending on what we want. For example, let's say if we're optimizing on the amount of floor area, we want to maximize that. Sometimes we're optimizing for structural stability, so we want to minimize the deformation. So whether to minimize or maximize depends on the task at hand. Then we have the solvers tab. This is basically where the optimization is happening. Galapagos is offering two types of solvers. One is the evolutionary one, and the other one is called simulated annealing. We're going to be using the evolutionary one in this tutorial. And then in record is a log of all the species, of all the individual solutions that Galapagos created once it starts running. Okay, let's hit cancel here and prepare the genome to pass to Galapagos. So let's enable this part of the definition. Here we go. And what we want to do first is revisit how our tower design is defined. For Galapagos, we only need to define one solution at a time. Galapagos will take care for creating the thousands of solutions, thousands of design options for us, so we don't need to do the cross-referencing, we don't need to numerically describe all the possible options. And basically, our tower is defined by 8 numbers, and we can use a component that comes in with Galapagos, which is called the gene pool. Here's the gene pool, and I can right-click and edit to say that we want that to be between one minimum of 1 floor and maximum of 110 floors. Here we go. So all in one. And we don't want 9. We want... we don't want 10, we want 8. So this is the gene count. So 8 is 8 tubes. And now we want to find the height of the 9th tube, which happens here. So basically I am going to pass that here, and at the end we should have, basically we need to flatten that again. Flatten. Yeah, at the end we will have a list of 9 values, so basically we don't need that anymore, that part here. Here we go. From then on, here's our genome, how we describe the building. Here's how we pre-filter it. We don't pre-filter it anymore. We are directly going to connect, instead of the 5 selected designs, we're directly going to connect the genome here. So let's see if that works. Basically, if it works, we should have only one design. Yeah, one design, one is displayed, and it should be controlled with these numbers. Yeah. So this is our genome that defines the building. The analysis still works, and the display interface still works. So let's keep it there for now, even though we don't really need that, because it's only going to be one option at a time displayed and generated. So let's go back here and take the Galapagos closer to the genome. Here's how you connect it. As you see, also the wire looks differently here. So that means that this component is now driven by the Galapagos optimizer. And now we need to do something about the fitness. As I said, it only needs one number. So, and we have 4 numbers. One way to deal with that is to choose which one of the numbers is most important for us, and all the other metrics will be ignored. And the other way to deal with that would be to create a formula which takes into account the dependency of each of these numbers. So just so we have something running as soon as possible, let's find the tower with the maximum area. So let's connect the fitness component to the area, but as you might see, Galapagos doesn't accept integer numbers as fitness. It needs to be a number. So let's pass the area to a number component and connect it. Okay, now it's connected, so it's a green line. And basically, we can now double click, say we want to maximize, yes, switch to solvers. Let's take a look at what's happening here and start the solver. we won't see nothing at the beginning, some numbers here, some dots and so on. If we switch on this one, we are going to see the design option that's being evaluated at the moment. So Grasshopper does all this number crunching for us using Galapagos, and we don't have to pre-calculate all the shapes and all the performance metrics. It does it one at a time, and we already know what the answer is here, right? All tubes are with the maximum height. But this is just for illustration purposes, and let's see how quickly it will find that solution. If you press the radioactive button here, you're actually introducing mutation into the population that's currently being evolved. Sometimes that helps to speed up things converging to the optimum we're looking for. So it's still running, and then what we see here is all the individuals that we can reinstate later on by selecting one of them and click reinstate once the solver is done. And basically this is the setting on the sliders. We want to end up with an individual that has this as a straight line at the top, so every slider is at the maximum. This is the perfect illustration of how stupid computers can be, because it takes it so much time to arrive at the optimal solution, which we already know what it is, the 9 tubes with the maximum height. But at the same time, here it's only about one criteria, one metric. Once it's more complicated and we have 4 metrics that are in conflict with each other, so minimizing the overshadowing of the park goes against maximizing the floor area. The computer can actually help us find an optimal solution that we cannot foresee so easily. Let's introduce some mutations and see if it will get out of this local optimum where it is. Yeah, I think it's getting closer. Look, almost everything is at the maximum now. So let's introduce a bit more mutation. Okay, so that's pretty close now to the optimal design. We can stop this illustration here, and let's see how we can combine all the 4 metrics into one formula. So let's stop the solver. And like I said, we can choose one of these designs and click reinstate. So it will be reinstated, which means that the sliders in the genome will be set. Where's the genome? Here. Will be set to the ones that produce that individual. So here we have different designs that are close to the optimal. Okay, so much for that. Okay, now let's see how we can combine. So this is our number, this is the fitness. This is the fitness that at the moment is connected only to the area. Let's see how we can combine all the 4 metrics into one. First of all, let's bring all of them here. So this is the fitness. Then let's take the area. Here it is. Then the other metric is the shadow over the park, which is here. So let's take that one. This is park shadow. And this one is the neighbor shadow. Let's connect this here. Let's ignore the total shadow area, which is kind of irrelevant for now. And that would give us not 4 but 3 metrics, which we want to use to constitute our fitness. Okay, so we want to maximize the area. So we will be maximizing our fitness as well. And how can we convert the park shadow, which currently is less is better? The park shadow is measured in square meters. How can we convert that into something that can be maximized? We can think of it like this. We want to maximize the area of the park that is not under the shadow. So in order to do that, we need to know what's the area of the park and then subtract from that the area that is being overshadowed. So the area from the area of the park we can get by measuring the park outline, which is here. Measuring the area of the park outline. So this is the area of the park. Let's do number, park area, and let's do the same for the neighbor. The neighbor is also going to be measured in the same way, so that we can convert the relation into optimizing for the maximum. So the park shadow and the park area, we can subtract them. So subtract the park area, subtract the park shadow from the park area, and in order to make that a coefficient, let's divide it by the park area, the total park area. So divide this number by the park area. So basically now we have something to multiply our area with here as a coefficient measuring how well our building design is performing on the park shadow metric. If this is 0, then this will be 1. Let's call that, let's take in the number, and that would be park fitness. If the park shadow is more than 0, then the park fitness will be less than 1. And if we multiply it, so let's multiply the area with the park fitness. So if this is less than 1, means our design is not performing so well on the park shadow metric, we are going to penalize the design area result. So if we have two designs with similar areas, but one is overshadowing the park, that would be penalized with the coefficient, and then the one that's not overshadowing the park will have a higher score. So basically that would be our fitness now. Now let's do the same for the park. We are going to copy this part of the definition. So we are multiplying, we're subtracting the park shadow. This says park shadow, but yeah, that's not park shadow, that's the neighbor shadow. It's connected correctly, but it has the wrong name. Okay, neighbor shadow. So we're going to subtract the shadow over the neighbor from the neighbor area. Then we're going to divide this result by the neighbor area to establish the neighbor fitness. And we are going to multiply that as well into the fitness. So now if we have a design that has 0 overshadowing over the neighbors, it will be represented by its area. And if we have a design with the same area that's overshadowing either one or both of the neighbors, it will be penalized with a coefficient that's less than 1 into the final fitness. So that should give us already the relation we want. We want to maximize the area but minimize the shadows. So double click, maximize the fitness, and start the solver. And if we switch on this mode, we are seeing each individual as it's being evaluated. So let's see what that would give us. As we can see, the design is already converging to some optimum, where the corner tube is quite low, so that it doesn't overshadow the neighbor. And here it still actually is not accounting for the shadow over the park. Let's introduce some mutation to the system to get it out of this local optimum where it was. And let's hope it finds something. And this is again a perfect illustration of how this optimization is a human-guided process. You actually need to know at least what a good solution looks like, and guide this process and not rely on the computer blindly to give you a design. So keep your critical architectural thinking always on. I'm going to introduce some more mutations here. And what the chart here above shows us is the top line shows how well performing is the best design in each particular population, and the bottom line shows us what's the fitness of the worst individual in that population. One population consists of 50. Here population is 50, and the way this works is that for each population 50 are generated, evaluated, sorted, maybe 10, or what's the rate? Maintain 5%, so 5% stay, move on to the next generation and get to reproduce the top 5%. Okay, what it found so far is that if it minimizes the neighbor shadow, at least it gets quite a high score. Okay, it's about time to stop this now. So let's reinstate the top performing design. Here it is. Okay, let's give it another shot. I'm going to pre-populate the design with some local optimum. So let's take the gene pool closer to where our fitness is. So this is the fitness, and where our hypothesis. And then it wasn't optimizing well on the bark overshadowing aspect. So let's take a panel to take a look at this fitness criteria and this component, and then I'm going to artificially lower this one, yeah, just below the bark, so this can be the maximum. Then this one is also intersecting. I'm going to lower that here, and then this one is okay. This one we can lower so we can improve the performance on the neighbor. And let's leave it now at this as a pre-seed. And let's see what Galapagos does then with this information. So solvers, start the solver. Let's preview the options that are being currently evaluated and introduce some mutations. You see at the beginning it's jumping all over the place, but in later generations it converges to an optimum. Sometimes it's the optimum we want, sometimes it's not the global optimum, but a local optimum, so to say, which means that it thinks it found the best solution, but there is in a neighboring area a way better solution, it just doesn't see it. Okay, so it kind of begins to converge closer to the solution that we pre-configured it with. So here is a direct comparison between the two approaches, between the generative modeling approach, where we generate all the designs beforehand, and then using the sliders of the optioneering interface we can filter based on the matrix, and we have kind of way more control over what we choose and why we choose it. In evolutionary optimizations we need to set the right rules. Instead of choosing, we need to set the right rules so that the optimization goes into the direction we want it to go. It's definitely faster in terms of getting your first results to use evolutionary optimizations, but I think the generative approach, the optioneering approach, can deliver you results by keeping your freedom as designers. Okay, let's stop here. This looks good, and reinstate the top performing design, which is also what's currently being reinstated. So this is the top performing design, and what we can do is actually we can copy that genome. Let's click OK. Here down in our definition we can copy the genome of that design, copy data only, and we can paste it in the box here up in the optioneering UI. This is still disabled, but I can enable it, and at the end I'm gonna paste that design. So here we have a design that's not following this 30, 60, 90 row. It's the 6th design that we have. But if we activate that later, then next to the ones we found with the optioneering interface, we get also to get this one. Maybe we use the evolutionary optimization to find 2 or 3 other designs, and we have a nice, neat way to reinstate all of these designs so we can review them later on next to each other. Now, if we want to connect the other design to our evolutionary algorithm, let's copy this one, which is already made for evolution, and paste it down. Then we disable this, and we need the Galapagos. So let's connect this one. We need to reconnect this one, and this is the fitness Galapagos component, and that would be part 5, evolutionary optimization, alternative tower design. Okay, and let's move that, and then let's take the 3D model. So here is the 3D model for this tower. Let's move it down here. And the genome in that case is 6 positions that are moving between 0 and 3. So let's click edit, reduce that to 6 and 0 and 3. Yeah. So this is the genome. We don't need this. Basically we can use that directly like that. We don't need this. This part here is finding the highest number so that it determines the height of the core tube in the Sears design. So here we have this one. So this is our genome, and here we want to, yeah, and here we want to connect it as well. 6 lists, a list of 6 numbers, so that would be fast. And let's enable this design. The Boolean union fails because here we have only one design option. So let's flatten that directly instead of using the mapper. Flatten. We don't need this one. And here's our geometry. So this is the geometry. We just need to pass it to here. This is the design. So it gets evaluated. This is the 3D model of the Sears Tower. I'm going to delete that. And we said we want to measure the volume. So instead of copying, let's just do here volume, this volume, and that is our metric instead of the area. Here we go. That we don't need. And I think we can run the optimization. Everything else should be the same. Solvers, start. Let's preview what's being displayed. So we have a dancing tower here, stepping left and right. Let's introduce a bit mutation in the system and see where it converges to. Okay, I'm going to stop this after 15 generations. Stop the solver, reinstate, reinstate the best design. Alright, that concludes the generative modeling in Grasshopper series. I hope you get to use the skills you learn here in your design practice. If you create something with generative models or evolutionary optimizations, please share it in the comments below. It will be great to see what you've created.